In this video, we're going to talk about horizontal stretches and compressions. This is the most challenging transformation to talk about. And to help illustrate why it does what it does, we're going to use a sine function. Now, this is a trig function. This is definitely not a trig class. However, what a trig function does is it gives us a little bit of clarity that some of these other functions we have don't really give us. And so what I want you to see is this. Let me see here, make sure I do this ever so perfectly. The sine function is a wave. It is a wave, and it goes up, and it crests right there, and it comes back down through the x-axis. And it comes down here, and it lastly comes back up here. Now, this is one full wavelength. It starts at 0, starts at the x-axis, it goes up, it comes back down across the x-axis here, it bottoms out here, and it ends up back at the x-axis. This is the starting point. This is one complete wave, one complete wavelength. Now, please be very clear that this does in fact continue on back here, and it does in fact go back down this way. But what I have marked from blue to blue is one wavelength. The word for this is period. It's the period of this wavelength. How much space does it take to fill this? How much space it take for one wavelength to be completed? So from blue to blue, that is the period, that is the amount of space it takes to make one wavelength. Now, when we talk about horizontal stretch and compression, we're going to simply, and if you think back to what we did with vertical stretch and compression, it was a multiplication relationship, but it was on the outside of where x was. And a horizontal is going to be in there where x is. It's going to be something like this. F of x equals sine of 2x. Now, when you look at sine of 2x, the graph looks like this. It's there, 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 and then it goes up. Oops, lost my pen there. Goes up to there, back down to there, down to there, and back to there. So here's what I need you to see for the sine of 2x. You'll see the same basic shape that we had, but you may notice that it's happening faster. Here's what I mean by that. In the amount of space that it took us to make one wave of sine of x, you should now see two waves. And if I mark this right here, that blue, you can see that from this first blue to here is one wavelength, and then from from that blue over to the end is another wavelength. There are two waves. That's a wave, and that's a wave. There are two waves, two full wavelengths in the same space that I used to have one wavelength. So when I see this 2 right here, what it's telling me is that in the same space I used to fit one wavelength, I now fit two. Now what's weird about that is that the waves actually got smaller. So if I look at this first wavelength, this first wave, it is half the size. Because I can fit two waves in the same space, each one is half as big as it once was. So as weird as this is, when I multiply by 2, the net effect is that this actually is a compression. So this right here is actually a compression. It makes it smaller. It fits 2 in the same space that 1 used to fit, therefore it's half as big. So we oftentimes would see something like this. We would see f of x, this is the general case, sine of bx. And when you see that b right there, that b represents the stretch compression. But it's actually the inverse. It's the multiplicative inverse of what you would expect. So when we see 2 right here, when we see this 2, what that's actually telling us is that the waves are going to be half as big. And so when you look at B, the way we talk about B, if B is greater than 0, that's actually going to be a compression by a factor of 1 over B. It's the multiplicative inverse. So if I had said, what if I had said this? I had said sine of 3x. Hopefully, intuitively, you can feel that sine of 3x. And that would literally mean in the same amount of space that I have the original sine of x wavelength, I would now have 3 waves in that same space, which means each one would be 1/3 the size. So a sine of 3x would be a compression by a factor of 1/3. Now, where this gets more interesting is, what if I were to say f of x equals sine of 1/2 x? Well, it actually fits this description pretty well. So here's the deal. If 2x means I fit 2 wavelengths in the original space of 1 wavelength, sine of 1/2 x simply means this. I can only fit half a wave in the original space, which means I only get this first half, this first hill. Oops, I'm not drawing this very well. Now, that's that first hill. So that corresponds to, say, this right here, this up and down. But in that case, I only can fit that first piece in the same space it took. Now, certainly, this would stretch out very slowly. And what I get actually is a really elongated wave, a really long wave. So when we look at things like sine of 1/2 x, it also is a scale factor, but it's also the inverse. It's also the 1 over b. So what we have then is sine of 1/2 x is actually a stretch by a factor of 2. It is going to be twice as long as the original wavelength. So when you have a number being multiplied on the inside, right there, with that x, it is going to be a stretch or compression, but it's going to be the multiplicative inverse of the number that's actually there. So when we had sine of 2x, like right here, that was actually a compression by 1/2. Sine of 3x would be a compression by 1/3. And a sine of 1/2 x would actually be a horizontal stretch by a factor of 2.